By investigating the soil of an area, you can figure out how long it's been a surface that's exposed, because the longer it's been there, the more developed the soil will be. So that tells you quite a bit about the weathering of the area. Soil layers are described as soil horizons, and they're assigned letters to indicate the different properties that they have. The top layer is the O horizon. That's an upper organic-rich soil horizon composed of dead leaves and other plant and animal remains. So when you think of, for example, a forest floor or anywhere where you have a lot of leaves falling down on the surface, that breaks down and you're creating a layer almost like mulch or compost, where things are breaking down. You've got a lot of pieces of plant material and all sorts of living things. Just below that organic material is the A horizon. The A horizon is topsoil composed of dark gray, brown, or black organic material that is mixed with mineral grains. So you have a combination. It's not just organic material. It's a mix of those organics that are very nutrient rich, that makes it great for plants to grow in, along with mineral grains. So along with sand, along with clays, it's all mixed together, sediment and organics. Depending on the area and the conditions for the soil, you won't necessarily have all of these layers. With that in mind, the next layer down is the E layer. This is the leached zone, a light-colored leached zone of soil that's lacking clay and organic material. Below that is the B horizon, a zone in the soil characterized by the accumulation of material including iron oxide, clay, and calcium carbonate, depending on the climate and the starting material. So what were the minerals that were there to begin with? That will determine what you'll find in this zone. And finally, below that, we have the C horizon, weathered bedrock. It's a zone in the soil composed of weathered bedrock or sediment, grading downward into unweathered bedrock or sediment. When I say grading down, what I mean by that is we're changing the size of the sediment. So you start out with smaller pieces of the bedrock higher up. The pieces get larger as you get closer to that original surface of the bedrock that was being weathered. So the bottom line here is that soil consists of weathered rock plus material from the atmosphere, decaying plants, animals, and microbes. It's a lot more complicated than just here's a bag of soil that I purchased from the home improvement store. All soils are not created equally. They're not all great for growing things in, and they're different for many different environments. For different climates, you'll have different types of soil, and for different spans of time, you'll have a different development of soil. When we look at processes of soil formation, we have two main things going on. We have the origin of the material, where material comes from, and we have the mechanism for movement, so how material moves. Looking at where material comes from, water, organic matter, and sediment from the surface are closest to the surface. They're in the upper horizons. As we move down to the lower horizons, we're looking at gas that's being given off by plant roots, and furthest down we're looking at weathering that is weakening underlying bedrock. So as we have groundwater moving through, it's breaking everything down. Okay, the process of weathering is going on through this entire column. And then when we look at how material moves, we have ions right? Just charged particles, ions that are leached from the upper part as water flows downward towards the water table. It's leaching away nutrients, and then clay and fine particles work their way downward. So the smallest materials are actually being transported further down. And then we have calcite accumulating only in desert climates, in very dry climates, and that's where you get a buildup of caliche. We know that different climates have different types of soils that result from those climates. Looking at this example, we are examining the soil of a tropical climate. So if you look at a typical tropical environment, you might see quite a bit of vegetation and think, hey, I bet they have really nutrient-rich soil here. However, it's just the opposite. Because they have such high rainfall, a lot of those nutrients just get stripped right out of the environment. So if you look at the soil horizons here, we've got a very thin layer of organics. We've got the A horizon, and we don't even have the E horizon. There's no leached area because the whole area has been leached out. There's no place that it's coming out of in particular or building up. It's all being removed. So abundant rainfall leads to intense chemical weathering and washing material out of soil. You end up with lots of clays and leached materials. The temperate climate ends up having a more enviable soil situation here. The temperate climates are cooler with less rainfall, so examples would be grasslands, forests, typically where you would expect to find farms. There's enough moisture to leach soluble material out of the soil, but it's not so intense as the tropical region, so you're not left with just leached materials, but you have the E horizon here, a much more nutrient-rich, darker organic and A horizon in this area. So this is ideal for growing. Here's a more familiar example of soil. This is from arid climates, so dry, generally hot climates, much like ours here in Phoenix. There's less chemical weathering, and material leached from the upper parts of the soil accumulate farther down. Calcium carbonate or calcite precipitates in the soil, building up over long periods of time and forming caliche over tens of thousands of years. So if you have a zone of caliche underground, you know that this has been an arid climate that's been building up this calcium carbonate for tens of thousands of years. You'll also notice that we do not have all of our horizons here. We've got the A horizon, B horizon, and C horizon. There is no organics horizon. We don't have enough vegetation to be building up and accumulating organics on the surface, and we do not have the E horizon either because we don't have enough water constantly flushing through this area to be creating a specific zone that's been leached. Because soil takes so long to develop and is so essential for growing crops and the health of the water table, soil is really quite a valuable commodity. So any area where nutrient-rich topsoil is being removed needs to be examined to make sure that that doesn't happen. So here are four main ways that soil is threatened. This first image is from Namibia in southern Africa. It's overgrazing by cattle. So this is certainly not specific to Namibia. This is very common in the U.S. And this is why a lot of people have problems with people allowing their cows to graze over wide spans of land. While the cows have to eat, when this happens, when an area that does not have enough vegetation gets overgrazed, when there's not enough for the cows to eat, there are too many cows and not enough food, they end up tearing up the area, and in the process they remove the vegetation, remove the roots that are holding the topsoil together, and then it allows that topsoil to just blow away because it no longer has the plants and their roots holding together all of that nutrient-rich soil. Then one just below that is removing vegetation. So this image, we're looking at clear cutting that's occurring on Mount Rainier in Washington. So they cut all of these trees down, and as a result, just like with overgrazing, the root systems are no longer there to hold the soil together. The plants are not there so that groundwater can slowly infiltrate. You end up getting quite a bit of runoff, and that just removes all of that topsoil that's taken thousands of years to develop. Then if we look at the upper right, the example we're looking at is in Peru, where they've cut terraces into this hillside to try and prevent erosion. Erosion is a natural process, but if climate changes, things dry out, we're losing vegetation that was holding it all together, or we have some sort of other change in precipitation, we can have excessive erosion going on that takes our valuable soil away. So it washes down the hill instead of staying in place. And the bottom right, soil contamination is a huge threat all over the U.S. and in Mexico and really around the globe, but particularly where we have a buildup of pesticides. So what we're looking at here is a picture from Colorado where we have a salt buildup and pesticides. So when we say salt, I should put it in quotation marks because it's not sodium chloride like you would find in the ocean or in your salt shaker, but rather it is a combination of soluble minerals that end up contaminating the soil, that are part of irrigation water, that are coming off of fields that are being watered that have pesticides, fertilizers, and herbicides as part of them. Some other problems related to soil include liquefaction, swelling or expanding clays, and soil compaction. In the example of liquefaction, all the way on the left, it has to do with seismic activity and soggy sediments, essentially. So shaking, the movement of seismic waves through sediment, causes sediment to lose grain-to-grain contact and strength. So the sediment actually begins to behave like a liquid, and liquids will come up to the surface. So groundwater comes up to the surface, and any sediment that's fine enough comes up to the surface as well. And there can be huge implications to that. We can lose stability under buildings and fracture other structures. Swelling clays. The image that's shown here is a road that's destroyed by swelling clays. So clays are essentially a bunch of little minerals that are loosely packed together, and they can hold quite a bit of water. This is not a compacted clay, right? When we're talking about permeable and impermeable layers, we talk about compacted clay as being impermeable. Before you compact it, it's loosely consolidated, and clays incorporate water between sheet structures, which allows swelling when wet and shrinking when dry. So you can imagine if the the ground underneath your house expanded, it offsets your foundation, it offsets roads, it can cause all sorts of structural damage. And then lastly, soil compaction. The compaction of clays and other sediment can cause the ground to subside and not necessarily all in one even surface. So you can get one area that's compacting or subsiding more rapidly than surrounding areas, and that causes offset and fracturing in structures.